Imagine waking up one morning not to the gentle glow of the sun but to an overwhelming silence. The birds are no longer singing, the wind no longer whispers through the trees. You take a breath but it feels thin, empty, and unsatisfying. This isn't a scene from a science fiction film. It is a glimpse into a real chapter of our planet's history, a time when the very air we depend on almost vanished entirely. Earth, our vibrant blue marble, once faced a catastrophic crisis where its precious oxygen levels plummeted. The sky would have turned a strange hazy color and the oceans would have suffocated. It is a story written in the oldest rocks, a forgotten drama that played out over millions of years. This event, a dramatic rise and fall of atmospheric oxygen, reshaped the course of life on our world. It serves as a profound reminder that the stable, breathable atmosphere we enjoy today is not a given. How can we possibly know what the air was like over 2 billion years ago? The answer lies not in the sky, but deep within the Earth's crust. Geologists are like planetary detectives and the rocks are their witnesses. They examine ancient sedimentary layers which were once the muddy floors of primordial oceans. These layers hold chemical clues, frozen in time, that tell a vivid story of the world above. One of the most important clues comes from elements like iron. When iron is exposed to oxygen, it rusts. You can see this on an old car or a forgotten nail. In the ancient world, this simple chemical reaction happened on a global scale, leaving behind a telltale signature. For much of Earth's early history, the rocks tell us there was virtually no oxygen. We find deposits of minerals like pyrite or fool's gold in ancient riverbeds. Pyrite crumbles into dust in the presence of oxygen, so its survival means the atmosphere was barren. Then, around 2.4 billion years ago, something extraordinary happened. We begin to see the emergence of banded iron formations. To understand how the air vanished, we must first understand how it appeared. For the first 2 billion years of Earth's history, the atmosphere was a toxic cocktail. Methane, ammonia, carbon dioxide. Life existed, but it was simple and single-celled, living in the oceans and hidden from the sun's harsh UV. These microbes were anaerobes. They thrived without oxygen. To them, it was deadly. The world belonged to them, a quiet, murky kingdom where evolution crawled along. The revolution began with a tiny hero, cyanobacteria, a humble microbe with a radical new trick. It learned photosynthesis, using sunlight, water, and carbon dioxide to make energy. Sunlight, water, carbon dioxide photosynthesis produced a revolutionary byproduct, oxygen. At first, oxygen was a local pollutant, reacting with iron in seawater and sinking to the ocean floor. Those reactions built the banded iron formations, the first sign of a planetary change. The cyanobacteria were unknowingly poisoning their own world and setting the stage for ours. For millions of years the process continued. The oceans acted like a giant sponge, soaking up oxygen. Oxygen began to bubble out of the water and escape into the atmosphere. The Great Oxygenation Event, a transformation unlike any other. The new oxygen-rich world seemed poised for greatness. Following the Great Oxygenation Event, life exploded in a flurry of activity. The Lomagundi-Jatuli event, recorded in those unique carbon-rich rocks, tells of a time when the oceans teemed with photosynthetic life. These organisms were so successful that they drew enormous amounts of carbon dioxide out of the atmosphere, burying it on the seafloor as organic matter. This biological boom pumped even more oxygen into the air, perhaps reaching levels similar to what we have today. For a time it must have seemed like a permanent new dawn for planet Earth, a world finally made hospitable for complex life. But this success story contained the seeds of its own destruction. The very processes that created the oxygen-rich world ultimately led to its collapse. The massive boom in life was fueled by nutrients washing into the oceans from the continents, nutrients that were released by volcanic activity. However, geological activity is not constant. Plate tectonics began to slow down. Volcanism began to slow down. The supply of essential nutrients like phosphorus and molybdenum started to dwindle. The great biological engine that was pumping out oxygen began to sputter and starve. Without a steady stream of nutrients, the vast blooms of photosynthetic organisms in the oceans began to die off. As they died, the production of oxygen slowed to a trickle. The planet's oxygen budget tipped into the negative. The result was a catastrophic decline. The air, once rich and life-giving, grew thin and anoxic. This deoxygenation event was not instantaneous, it unfolded over millions of years. Oxygen levels plummeted to perhaps just 1% of their peak, possibly even lower. The rise of oxygen was a disaster for the planet's original anaerobic inhabitants, but the subsequent crash was just as devastating for the new forms adapted to air. Organisms that had evolved to use oxygen for energy, aerobic respiration, suddenly found their fuel disappearing. Imagine humans surviving on Everest but everywhere on Earth. Mountain cities like Denver, La Paz would become uninhabitable. Air travel would become impossible. Jet engines require vast amounts of oxygen. The global transportation network would grind to a halt. As oxygen levels continued to drop, effects would cascade through every part of society. At around 15% oxygen, people would experience confusion, fatigue, impaired judgment. Vigorous physical activity would become dangerous. Wildfires would become less frequent. Fire struggles to burn in low oxygen environments. But this is small comfort when simply breathing requires conscious effort. The very air would become our enemy. If oxygen fell below 10%, human life in the open air would be impossible. All complex animal life would face extinction. Fish would die as oxygen and water disappeared. Insects, birds, mammals, the world would fall silent. Only the simplest plants and microbes would survive on the surface. Our cities would become silent tombs, monuments to a lost civilization. The discovery of this ancient atmospheric collapse was not a single eureka moment. It was the result of decades of patient work by scientists from many different fields piecing together clues from across the globe. Geochemists were among the first on the case. They developed sophisticated techniques to analyze the chemical composition of ancient rocks. By measuring the ratios of different isotopes, carbon, sulfur, they could reconstruct the environmental conditions of the distant past. It was their analysis that first revealed the strange spike and subsequent crash in the carbon cycle during the Lomagundi period. These chemical clues were then combined with evidence from mineralogy. Geologists studying rock formations in places like Gabon, Finland, and North America noticed a distinct pattern. They found rocks from a specific time window, heavily oxidized and rich in organic material. Then, in the layers directly above, these features were gone. The story didn't make sense until scientists started to model the Earth's ancient climate and ocean chemistry. Computer simulations allowed them to test different hypotheses. The models pointed towards a scenario involving a temporary surge in volcanic activity, providing a feast of nutrients for life, followed by a long geological lull that starved that same life into submission. Simulations showed that a biological paradise, if not sustained by geological processes, could quickly turn into a barren wasteland, causing atmospheric oxygen to plummet. This convergence of evidence from chemistry, geology, and computer modeling painted a coherent, if dramatic, picture. The scientific community, through collaboration and debate, uncovered a lost chapter in Earth's history, revealing that our planet's atmosphere is not a one-way street towards more oxygen. Imagining a similar oxygen crash today is to contemplate a true apocalypse. Our modern world is far more complex and far more dependent on oxygen than the microbial mats of the Proterozoic era. If oxygen levels began to fall, even slowly, the consequences would be swift and terrifying. The first signs would be felt at high altitudes. Mountain cities like Denver and La Paz would become uninhabitable. Air travel would become impossible. Jet engines require vast amounts of oxygen. The global transportation network would grind to a halt. As oxygen levels continued to drop, effects would cascade through every part of society. At around 15% oxygen, people would experience confusion, fatigue, impaired judgment. Vigorous physical activity would become dangerous. Wildfires would become less frequent. Fire struggles to burn in low oxygen environments. When simply breathing requires conscious effort, the very air becomes our enemy. If oxygen fell below 10%, human life in the open air would be impossible. All complex animal life would face extinction. The oceans would become stagnant and stratified, toxic, sulfur-rich waters welling up from the depths. The sky might shift to a pale orange, a reddish haze. A primitive alien world would return, hostile to the complex web of life. The planet would transform. This is the scale of what we face in a similar crash today. Could humanity survive such a catastrophe? The challenge would be monumental, dwarfing anything we have ever faced. Survival would depend on our ability to create artificial, oxygen-rich environments. We would have to retreat into sealed habitats, biodomes built underground on the surface or perhaps even at the bottom of the sea. These habitats would need to be entirely self-sufficient, vast ecologies where we could grow food, recycle water, and most importantly, generate our own breathable air. Vast indoor farms of algae or other fast-growing plants could be used to scrub carbon dioxide and produce oxygen. Alternatively, we could use industrial processes like the electrolysis of water, splitting H2O into hydrogen and oxygen. This would require a colossal amount of energy, necessitating the construction of dedicated nuclear or geothermal power plants for each and every habitat. The survival of the human species would become a full-time engineering project. Life outside these sealed domes would be impossible without specialized equipment. Anyone venturing out would need to wear fully enclosed suits with their own oxygen supply. Not unlike the spacesuits worn by astronauts, exploration, repair work, and resource gathering in the outside world would be incredibly dangerous and resource-intensive. Society would be fractured, with humanity reduced to a handful of isolated pockets of civilization, each a fragile bubble of life in a dead world. The psychological toll of living in such a confined and precarious existence would be immense. The story of the Great Oxygen Crisis, buried in rocks billions of years old, is more than a geological curiosity. It is a profound warning. It teaches us that our planet's life support systems are complex and can be surprisingly fragile. The stable, oxygen-rich world we take for granted is the result of a delicate balance between geology and biology. Geology-biology. The ancient world tipped this balance and paid the price with 1 billion years of stagnation. Today we are tipping the balance again, not through nutrient cycles but through the rapid alteration of our atmosphere's chemistry. While our current crisis involves a different gas, the underlying lesson is the same. Radical and rapid changes to the atmosphere have profound and unpredictable consequences for all life on Earth. The planet has shown us that it can recover from such events, but the timescale for that recovery is geological, not human. Yet, within this stark warning there is also a message of hope. The story of Earth's air is a testament to the incredible resilience of life. Planetary deep freezes, asteroid impacts, near total loss of atmosphere, life adapted, evolved, endured. We are the beneficiaries of that incredible tenacity. We possess something no other species has had: consciousness. We can understand these ancient cycles and read the warnings written in the rocks. This knowledge gives us a powerful tool to make choices about our future, to protect the delicate atmospheric balance that allows us to thrive. The Great Oxygen Crisis is not just a story about the past, it is a lesson for our future. It calls on us to be careful stewards of our planetary home, to ensure that the air, once lost and regained, is never taken for granted again.